Okay, so what we've discussed is that when we have a limit at a point of a function of two variables, then as we approach, as we get closer and closer to that point on the domain, via any path that we choose to take, whether it's a straight line or a squiggly line or whatever path we take, if the limit exists, then along any path we're going to tend to the same value of f. If we find any two paths along which we get different values up here in f, then the limit cannot exist. Okay? And one way of relating to that phenomenon, a very useful way, which also allows us to calculate limits, is using polar coordinates, and it's a bit subtle. You have to be careful with using this theorem. I'm going to state this theorem, do an example, and then prove it. So the theorem says as follows. So let f be a function, fxy, be a function from R2 to R. Function, a scalar function of two variables. And we're going to assume, here's the assumption, that when we convert to polar coordinates, okay, just like you do in complex numbers, does everybody know what I'm talking about? Okay, so I'm going to replace x with r cosine of theta and y with r sine of theta. Okay, so when we write f in terms of r cosine of theta and r sine of theta, okay, then I get an expression in r's and thetas, but I'm assuming, this is an assumption, that it somehow breaks nicely into a product of one expression which has only r's in it, which I'm going to call capital F of r, times another expression which has only thetas in it. And we're going to see an example in a second. Okay? So this is an assumption. It doesn't always happen. It's a very particular case when it does happen. But when it does happen, then this theorem applies. Okay? So assume that this holds. And two more things. F of r, which is now a function of one variable, just the variable r, tends to 0 as r goes to 0. And g of theta, which is again a function of one variable, the single variable theta, is bounded. You all know what a bounded function is, right? It has some supremum, some maximal value which is or may not be attained, but it cannot exceed a certain value and cannot go beneath a certain value. Okay. Then the theorem says that fxy converges to 0 as xy goes to 0, 0. Okay? So let's first do an example and then discuss the proof a bit. And I just want to verify that everybody knows that what these polar coordinates are. So every, maybe let's write it here. So every point in the xy plane, suppose this is the point xy, any point, here's a point xy, I can express it uniquely by measuring the distance from the point to the origin, calling that r, and the angle that this line connecting the point and the origin forms with the positive x-axis. Okay? So any point xy translates into a point r and theta. Okay? Everybody knows this, right? This is really a review for everybody. Say yes. Okay. And the correspondence between x's and y's and r's and thetas is given by x equals r cosine theta and y equals r sine of theta. The reason for this being that if you form here a right triangle, okay, then cosine of theta is x. This is the distance from 0 to this point is precisely x, the x coordinate of this point, divided by r, by the hypotenuse, right? So x over r is cosine theta, so x is r cosine theta. And likewise, so this is x and this is y. And likewise, sine of theta is y over r, therefore y is r sine theta. Clear? By the way, if you want to go the other way, then how do we express r in terms of x and y's?
X tangent.
Give me one word in Greek starting with P, and it's a name of a person. Exactly, Pythagoras. R squared is x squared plus y squared. So r is the root of x squared plus y squared. Do you agree? Everybody? And the tangent of theta is y over x. So theta is the arctan of y over x. Okay, so this is how we go backwards, but right now we're going to use the moving from xy's to r's and thetas. Good? Everybody knows this, right? Okay, great. So back to our theorem, let's do an example. So here's an example. Let's look at the function, two-variable function in x and y. Again, it's going to be a case function, x squared times y squared divided by x squared plus y squared. This is well defined whenever x, y are not 0, 0. And if they're both 0, the function is going to be defined as 0. And I want to find the limit at the origin, at 0, 0. At any other point, I can, of course, use the fact that it's an elementary function. Just plot the point. Okay, just plug in the values of a and b, whatever they are. But at 0, I have to do a different calculation, right? What did I do wrong? Right, thanks. Okay, thank you. And I want to calculate the limit of fxy as xy goes to 0, 0. Okay? So what is this limit? So I'm going to use that theorem. Let's take a peek again at the theorem. The theorem says, convert to polar coordinates. Plug in r cosine theta for x, r sine theta for y. If it breaks into a product of one expression containing only r's and one expression containing only thetas, such that the r expression tends to 0 as r goes to 0, and the theta expression is bounded, then the limit of f is 0 at the origin. Okay? Let's see if this holds. So we're going to show that this is in fact 0. Proof. Let's look at f of r cosine theta, r sine theta. What do we get? So I'm plugging in r cosine theta for x, so I get r square cosine square of theta, times plugging in r sine theta for y, r square sine square theta, right? And dividing by, what's r x squared plus y squared? Right, I don't need to write this squared plus this squared because it's sine squared plus cosine squared is 1, or you can remember from what we just said that r is the root of x squared plus y squared. Right? So does everybody agree to this? Okay. Now, one of these r squared can cancel out, and we're left with r squared times cosine squared theta, sine squared theta. This is our f of r, capital F of r. This is an expression containing only r's in it. And this is our g of theta. It broke up, in this example, it broke up into a product of one expression containing only r's and another expression containing only thetas. Okay? No cross-contamination. Thetas and r's completely separated. Okay? That doesn't always happen. If it doesn't happen, you can't use the theorem. Clear? Okay. Now, what has to be satisfied in order for the theorem to hold? Does f of r go to 0 as r goes to 0? Obviously, it's just r squared, so this holds. Is g of theta bounded? Yes, because it's cosine squared, which is bounded by 1, and sine squared, which is bounded by 1. Do you agree? Between -1 and 1. So g of theta is bounded. G of theta in absolute value is less than or equal to 1 for any theta. Do you agree? So that's it. The theorem holds. We verified all the conditions of the theorem. When you write it like this, it breaks up. The two parts satisfy what they need to satisfy. Therefore, the limit of the function at 0 is 0. Clear? Okay. So what's going on behind this theorem? Why is it true? Okay, what just happened here? So I first want to discuss it a bit hand-wavingly, just to get the intuition, and then I want to formally prove it. This is like one of the single proofs we're going to do using the epsilon delta definition of the limit. But it's really an easy proof, a very easy proof. So what's going on here when we change to polar coordinates? What are we actually doing? So r, remember, measures the distance from the origin to the point, right? That's r. And theta measures the angle. Do you agree? Okay. And when it breaks up like this and f of r goes to 0, this is saying that as you get closer and closer to the origin, you tend to the value 0. Do you agree? And the fact that g of theta is bounded says that in a certain aspect, this tending to 0 cannot be overruled, cannot be messed up by g of theta tending to infinity or doing something funny. G of theta being bounded, something bounded times something that goes to 0 goes to 0. That's a Calc 1 theorem. Remember that theorem? Something bounded times something that goes to 0 goes to 0. Okay, that was true for single variable sequences or single variable functions. And that's the idea that's hiding here. Okay, so as we get closer and closer to 0, on a specific theta, we tend to 0, but it's kind of independent of theta. Okay, and what I said now is not exactly precise, and the proof is going to be precise, but this theorem, in fact, can be strengthened in replacing this g of theta is bounded, but by some other term that I don't want to go into now, but that is requiring less than g of theta being bounded, but still guarantees this phenomenon. Okay, it's somehow saying that this happens in some uniform way, this tending to 0. Okay, so this is really like checking what happens as you come along different paths, different thetas, and it's always going to 0. Therefore, the function is going to 0. Is the idea clear? That's just intuition. Good, everybody? Okay, let's prove the theorem. Let's prove the theorem. So, proof of the theorem. So, I want to use the definition of the limit. I want to prove that the limit of fxy is 0. So the limit of fxy equals 0 as xy goes to 0. Let me write what this means. Okay, 0 is now what L was in the general definition, and 0, 0 here are what A and B were in the general definition. Okay, so this happens if for any epsilon there exists a delta such that if the distance between x, y, and 0, 0, so x minus 0 squared plus y minus 0 squared, if this distance is less than delta and greater than 0, then f of xy minus L is less than epsilon. Do you agree that this was the definition? Right? Everybody with me? You're very quiet. Okay. So all these zeros are just in the way, so basically we can replace this line by saying the root of x squared plus y squared, if it's less than delta, then f of xy has to be less than epsilon. Do you agree? That's in the particular case where L is 0 and we're tending to 0, 0. Right? Okay. Now, do you recognize R here? Do you see R? Okay. So here's the proof. How do I start a proof? Let epsilon be greater than 0. Take any epsilon. I need to find a delta which guarantees this. That's how you prove it. Okay. Let's denote by M, capital M, the value, the bound of G, the value such that G of theta in absolute value is less than or equal to M. There exists such an M because G of theta is bounded. That's what it means to be bounded. Do you agree? Okay, so that's going to be our M. And further, we know that f of r goes to 0, as r goes to 0. Therefore, hence, there exists a delta such that if r is delta close to 0, this is single variable limit, if r is delta close to 0, then f of r is epsilon close to L, to 0 also. Okay, so there exists a delta such that if r minus 0, so just r, but r is always positive, so we don't need the absolute value. So if r is less than delta, then, and greater than 0, then f of r minus 0, so just f of r, is less than epsilon. This is just writing the definition for this single variable limit. Do you agree? Okay? Now, I want to replace this. Do you agree that since we know the existence of this limit, then for any epsilon we can do this, right? That's the limit. For any epsilon you can find a delta. There exists a delta such that pam, pam, pam. So I want to write this, but not for this epsilon, for a different epsilon, for epsilon over m. Okay? And let's do strictly less than m, so we're guaranteed that m is not 0. Okay? So do you agree that for whatever this epsilon was, divided by m, call that epsilon now. Since this limit is 0, there exists a delta such that if r is less than delta, the value minus 0 is less than epsilon over m. Do you agree? Okay, very good. Now, let's use this delta that exists. Let's use it. So, if, therefore, if x squared plus y squared is less than delta, greater than 0, the root of x squared plus y squared is less than, if this happens, I need to show that this happens, right? That's what I'm trying to prove. But if this happens, using this delta, this is precisely r. That means this happens, right? And since this happens, then f of xy, which we know is the same as f of r, which when we write as f of r cosine theta, f of r sine theta, breaks up into f of r g of theta. This is the assumption of the theorem. And let's write this in absolute value. equals this in absolute value. That's what the theorem states, right? That's the assumption. This we can in turn say equals f of r times g of theta, product of absolute values. F of r is now less than epsilon over m because r is less than delta. And g of theta is less than m. That's what m was. And that's epsilon. So we showed, using the delta provided by the convergence of f and using epsilon over m, using this delta, we showed the definition of the limit for f of xy. Okay? Good? Any questions? Okay. So it's kind of like a game proving these theorems using the definition of a limit. And it's a game that's sometimes not too difficult to understand when somebody else is performing it. Okay? But that's like many things in math. Okay? So, or in other things as well. Like if you watch this is an international class. I don't want to offend anybody, but if you watch Roger Federer or Nadal or I don't know, give your favorite tennis player playing tennis, that looks extremely easy, right? Well, what is he doing? He's doing this and this. Well, he's tall, he can do that, and it's easy, right? But try playing against him, right? You'll probably just get hit by the ball and fall 10 meters back. Okay, and likewise, looking at somebody swimming or riding a bicycle, okay, or doing math. Watching somebody do it is not exactly the same as being able to carry it out on your own, okay? That takes many times a lot of practice, a lot of getting used to, and it's especially true for this epsilon delta business. I assume you already found that out by now, right? Okay, questions on this proof? Anybody? Okay, so in contrast to what we said earlier, that if we want to look at just lines coming into the origin, that does not guarantee convergence, if we only look at straight lines. Under these specific assumptions, let's look back at the theorem itself. Under these very specific assumptions, it does suffice to look on these lines, on r's going to 0, okay? And in that case, we can say a positive conclusion that the function goes to 0, okay? In general, if it doesn't break up like this, you can't just convert to r and theta, check that r goes to 0, that f of r, that whatever you get goes to 0 as r goes to 0, and conclude that the limit is 0. Let's remark that. And the reason is that would just be saying, just checking that r goes to 0 is just checking along straight lines. So remark, writing f of xy equals f of r cosine theta, r sine theta, and checking that this expression, let's write, and checking that the entire expression goes to 0 as r goes to 0 does not prove anything. In particular, it doesn't prove that the limit of xy is 0 as xy goes to 0, 0. This is just checking. What does it mean that r goes to 0? It means you're fixing theta, you're not changing theta, and you're just taking the r to 0. That's exactly checking what happens when you approach 0 along a fixed straight line, right? So just checking that does not prove that the limit is 0. That's not enough, okay? You need actually to check that the assertions of the theorem hold, and they don't always. Okay? But, however, if for two different values of theta, we get different limits as r goes to 0. So if, this is just saying, ignore theta, take r to 0. If for one theta you get a limit, whatever it is, and for another theta you get a different limit as r goes to 0, that's exactly saying that when you approach along different lines, you get different limits. And therefore the limit doesn't exist. Okay? So if this happens, then the limit of xy does not exist. Do you know the abbreviation DNE? Have you used it? Does not exist. Have you used this? Okay, as xy goes to 0. Clear? Is everybody with me? Okay. So we want to move on. I won't do examples of this, but you will have enough examples to practice on where this happens or various things happen, and you have to understand what you can say and what you can't say. Okay? But basically, the only positive statement you can say is when all the conditions of the theorem are fulfilled, or you can modify the theorem and replace 0, 0 with a different point AB by shifting everything. Okay, you'll probably do examples like that in the tutorial. Okay, so this is for the discussion of R and theta, and that's the end of this one. Okay.